very much at Princeton. I've known for quite a while through Jan and some of the work. And then Chang Kim recruited him to join Barefoot, so I got some work and over the last few months. So the context of this is with all of this programmability being discussed for link brains, it remains to be seen whether it becomes widely used or widely deployed. But it's kind of interesting that the sorts of things that you might put into a programmable link brain. And I really like the things off the wall that didn't never thought of before, and out of left field. It tend to get so oriented in networking and thinking, I like this, but it's all streamlined and done. That's what the pioneers told us, and there's no complexity for the inside. But hey, that model has been totally destroyed in the last decade anyway. And people start to think about taking control of the network. People started to suggest rather mundane things like for load balancing and things like this into the plumbing. I think what we have glorified ranking. But what else could you do? One year has been working on gesture control algorithms that are very fast that run too many programmable switches. And other things might you do that. So this is one that really caught my eye a few months ago. And then over to you.
Good.
Thank you for being here.
Yeah, thanks. So, hey, everyone. So, today I'm going to talk about our new scalable, fast, and cost-efficient key-value storage system called SwitchKV. So, this work was mainly done when I was at Princeton, and was in collaboration labs and CMU. So most part of this talk is based on my presentation at the NSDI conference this year. And I'll also talk a little bit about how the new programmable network chips at Barefoot and the people languages would improve the previous SwitchKV design. I only have about 25 slides, so this won't be a very long talk, so feel free to interrupt me anytime. Okay. So key-value storage systems provide operations to store, retrieve, and manage key-value objects. So there are simple APIs such as gap delay form a fundamental building block for many large-scale cloud services such as Google, Facebook, Amazon, and many others. So these systems usually seek high performance. So ensuring high throughput and low latency is important, because many higher level applications rely on this key value storage layer to achieve high service quality. And it is equally important to keep the system cost efficient, because it decides whether the service is able to easily scale its performance and capacity as the data and demand keeps growing at high rate. So the goal of our key value system is to offer both high performance and low cost operations. However, it is challenging to achieve this goal under the real world workload of many cloud and big data applications, which share some similar characteristics. So first, the data volumes are usually huge. So the cost to store this data actually matters. On the other hand, the size of each object is typically small, such as 1,000 bytes for thumbnail images, 100 bytes for Twitter messages, or only a few bytes for some system parameters. For example, in the Facebook memcache workload analysis paper published a few years ago, they said that almost 1/3 of their key value queries only ask for 2 byte values. So these objects are usually randomly accessed, which means the workloads are highly I/O intensive and would be ill-served by conventional disk-based storage systems. And the workloads are massively parallel and with many concurrent and mostly independent operations. So what's worse, many workloads have power law access distribution, where a small portion of the key accounts for the majority of the queries. And sometimes these hotspots could change very quickly. So these highly I/O intensive, concurrent, skilled, and maybe faster changing workloads pose some major challenges to scaling the system capacity and the performance efficiently. So let's take a look at a few of the major challenges and also the design objectives of our system. So first, how to use DRAM and flash storage efficiently so that the system can meet the performance capacity and these kinds of requirements with minimal cost. So Switch KV is actually a scale-out design for flash-based storage cluster with key value data and hash partition across the storage nodes. So given the performance requirements, some current storage systems keep data entirely in memory with disk used only for failure recovery. Some other systems put a significant portion of data in the cache to achieve high hit ratio and high performance. So those systems that aggressively use DRAM are both expensive and power hungry. So meanwhile, flash storage is 10 times cheaper and 100 times more power efficient than DRAM. And some recent advances in the flash storage technologies such as NVMe and the optimized software stacks are opening up new design, new points in this design space of the storage systems. So it is now possible to build a flash-based key value storage cluster that can meet the performance goals of many cloud services cost efficiently. So this would lead to significant cost savings, especially for services that require the data to be persistently stored anyway. Another challenge is to how to ensure dynamic load balancing as the cluster scales out, so that the system can fully utilize the storage servers regardless of the workload distribution. And the third challenge is how to achieve maximum parallelism in multi-core systems so that each individual server can fully utilize the processing power of modern CPUs. Switch KV meets these challenges with new architectural design and algorithmic optimizations. And our core benefits comes from our use of faster programmable networking. And this will be the focus for the rest of this talk. So as I just mentioned, key value workloads for cloud applications are often skewed. Some small number of keys can be much more popular than others and make the load across different nodes imbalanced. And the workloads may change quickly. All these pose challenges to scaling out the key value cluster. So without proper dynamic load balancing, most servers in the cluster would be either over or underutilized, which leads to very poor performance and efficiency. So even a single node being overloaded could have a huge system-wide impact because the system service quality is often decided by the tail latency, which means the system would be bottlenecked by the single overloaded slowest node. Therefore, even though for many systems, the aggregated service level agreement in terms of throughput and latency is fixed, the service provider may still have to substantially over-provision the resources for each node in order to handle this dynamic and unpredictable workload skew. So even though most of the times, the actual workload will be far below that, increases the system cost. And traditional dynamic load balancing methods often keep migrating data around and replicating data. So they are usually too slow to handle rapid workload changes and often introduce high system overhead and consistency challenges. Instead, Switch KV applies a new approach that could be more effective and efficient. Actually, caching can be an effective dynamic load balancing technique for hash partition key value clusters. The intuition is that if the workload is near uniform, load across the backend are balanced. And if the workload becomes skewed, then the front-end cache can absorb the hottest queries and still keeps the load across the backend well balanced. So it has been proved by our previous work that if the data is randomly hash partitioned across the backend servers, then the cache needs to only store the order of unlocked and hottest atoms to guarantee good backend load balance, where n is the number of backend nodes, not the number of objects. For example, we can have a cluster with 100 backend nodes to store like billions of atoms, and only need a single cache with 10,000 entries to keep the load across the backends always well balanced. So based on these theoretical results, we built our system as a heterogeneous key-value cluster with many cost-efficient flash-based backend servers that are provisioned just for the performance goals, and one of a few high-end cache servers to serve the small number of hottest keys. Note that this rapid provision of the backend cluster would lead to huge cost savings by the system design, because you do not need to provision or estimate for the peak load.
Have you any assumptions to do with the distribution of queries? Like you mentioned that queries were skewed as the result in your previous work.
It's actually not my, it's my collaborators' favorite reason in the CMU and the Intel's previous work. Yeah. So basically, the assumption is that if the backend, if the data across backend is a partition based on the key hash, like so consistent hashing, and if you have the very fast front-end cache with this all of cache atoms, and if a query so key will not exist, so the load of the query for single key will not be more than like the capacity of a single backend node, which is not a strong assumption. Then this it's published 5 years ago in SLCC. So, however, it is actually challenging to build an efficient real system for this. So we are mainly facing two problems. So the first is how to efficiently serve queries with cache and backend nodes. And the second is how to efficiently update the cache under the dynamic workload. So next, let's see where these challenges come from and how to use them. The traditional caching architectures are not good fit for our system. Because in both traditional look-aside and look-through architectures, clients always send queries to the cache. And the cache has to process all queries and handle cache misses by either reporting back to the client, like client to resend the query to the backend, or redirecting the queries to the backend. So this could be a serious problem for our system, as our cache is small and only serve a small portion of the queries, mainly for load balancing purpose. So the cache hit ratio could be low. A significant portion of queries goes to the backend. Then the throughput will be bottlenecked by the single cache node, and the latencies for many queries will be high because they need to go through this multiple round trip and the machine trap. And what's more, the on-pass cache node load balancer in the look-through architecture could be the additional critical failure point in the system. So prior research from the Microsoft data center can show that these servers are much less reliable than networking devices. So to solve these problems, we need to remove the redundancy in the query paths. Our system switch PV explores programmable OpenFlow switches to enable content-aware routing in the network. So clients send queries to the switches. Switches route them directly to the right node at line rate based on the key information encoded in packet header. So in this way, the latency can be minimized for all queries because all responses will get back in one round trip. And throughput can scale out with the number of backends without being bottlenecked by the cache. And the system availability will not be affected by the cache node failure.
So you actually have only one cache node?
Hmm?
You assume you have only one cache?
The current prototype is only, but we can have like scale design with multiple small cache nodes, but the number of cache could be like significantly smaller than the number of that. So it's basically a small cache. As I said, like you only need to, so the cache size is determined by the backend node.
I mean, you must have like using OpenFlow Switches then, because you need to decide what to send the request like. But since you're using the switches, you can put down the policies and you can let the switches make the decision which cache to send.
Yeah.
Right? So
Yeah.
it probably becomes easier for one.
So if one cache is not enough, we can certainly deploy more cache. Like it really depends on the cluster size.
What fraction of the load goes to the cache?
Hmm?
What fraction of the load goes to the cache?
Oh, it really depends on the workload distribution. If it's each skew, like if 99 workload, like not like half or even more, like queries may go to the cache, and with the workload like changing, and if at some period the workload is more smooth, more evenly distributed, so only a small portion of the queries goes cache, and it will be well served by the backend. It's balanced load balanced. So the cache is only to absorb the hardest queries in terms of this unpredictable.
So have you looked at that trade-off between number of caches and latency? Like that, obviously there's a trade-off. The size between the size of the cache and latency.
Well, we only need a very small cache, and actually for
Okay, so what is small? I mean,
small, as I said in the list, so the number of cache atoms is only like order of a lot. Let's say if we have, in this example, if we have hundreds of a big cluster with hundreds of cache atoms, we only need a cache with 10,000 entries. It can, for very small values, it could even be possible to fit in the average.
And how big is how big should we think an entry is?
But that's then the workload is like for the.
But I imagine that the process is trying to get to the question how practical this seems in an element, a network element that's not likely to have much storage. So it's useful to have an idea.
Yeah.
Are we talking about hundreds of gigabytes? Or are we talking about?
Yeah. So like actually in this switch QB product, we I would say the actual data, the value is stored in the cache node. So in the switches, it only remember some like a key cache or key digest, and do this content-based routing. Like if you have 8-byte cache key, then you can easily support like more than 100,000 keys.
Where is the content stored? I'm sorry, I misunderstood that at the beginning. So where is the cache entry itself? So
the cache is stored in another cache server. This is different from like what we talked because
I'm just trying to understand because I think this is what the question is. I only get an idea of what's stored where.
Yeah, the cache server, the high-end cache server stores all the actual data, and the switches only store only needs to know that match on some cache, match on the key or key hash, whatever, and send the query directly to the cache.
Or the basic one. So switch knows what content of cache.
Yeah.
So how to use that?
As I said, like if you need 8 bytes for each key, you can really support more than 100 keys in the switch. Yeah. I'll talk later about the update mechanism. Okay. So here's some details of the design based on the previous work to explore the SDN and switch hardware. So to enable this content-aware routing, the clients encode key information in packet headers. And in order to decide whether to route the queries to cache or not, so the switches need to keep the forwarding rules for each cached key. That's some questions you got. And so this means the forwarding table size will be at least as large as the cache size. So the current OpenFlow switches, switches can use both TCAM or L2 tables for packet processing. So the TCAM table is able to perform flexible wildcard matches, but it's really expensive, power hungry, and thus the size of TCAM table is very limited. I mean, while the L2 table, you're sitting SRAM and can perform exact match on the addresses, it's cheaper and more power efficient. Modern commodity switches can support more than 100,000 L2 entries. So this size is actually large enough for our small cache to ensure good load balancing. So therefore, we encode the key hash in the destination MAC address for real queries, and maintain exact match rules for each cached key in the switch L2 table. And each client also tracks the mapping between the key space partitions and the backend nodes, and always use a destination backend IP address. Do not stick to the existence of the cache node. And the switches maintain the forwarding rules in TCAM tables and matching with IP addresses. So when a packet comes in from the ingress port, we'll first look for exact matching the L2 table. If there's a match, it means that the query is for cached key and will be sent to the cache node. And if it's not, we'll look for matching the TCAM table, and the query will be sent to the corresponding backend nodes. And in the SDR paper, we also have some in-depth discussion of how to deal with rare cache misses caused by the cache collision or temporarily outdated forwarding rules, and how to scale out the system with multiple switches. So hopefully now you agree with me that this is an interesting idea to use OpenFlow switches to do this content-aware routing. But I'm pretty sure that many of you may have. I'm sorry. Yeah.
So how does it get routed before?
So we basically that we are assuming that we have full control over the host, and we can modify the address, and we have full control of the routing policy using OpenFlow switches. So we can.
So you would have to put every hop along the way.
Yeah. Yeah, all we need is encapsulations and stuff. That's what I'm doing. Yeah. So. Okay.
So if you're going to use this data in such a way, is there work that the cache was previously run that now no one was done, or have you just pushed what was previously the cache's function, which is to identify keys and misses, and just pushed it onto a switch?
Yeah. So basically for cache, you need to cache lookup to see if this key is in cache or not. Right? So we are basically push this part of the function to a switch so that all the queries can directly go to the right node, and they can run it.
So we haven't reduced the total kind of work. Moved it to
Yeah. Okay. So this has been already brought up. So I got all of these kind of questions at the NSDI, well, you're modifying the MAC address. So the L2 is so fundamental that can you really change it? Or is it realistic for production systems? And so you cannot use my regular socket of the raw socket of DDK. And who knows the side effects of other network application behaviors. So I didn't have good answers to these questions when I started this project. But now we have a way to solve all these problems by using the P4 switch. So here with a honey flag, I see many of you have already know like the basic idea of P4. Okay, so I'll go over so like P4 is a language for like a processing for expressing how the packets are processed by the data plan of programmable network processing systems, which can be like network cards, FPGA switches, software switches, and high-performance programmable ASIC chips. And here we focus on the P4 network chips with fully user programmable data plan. And we can define new packet format and describe our own packet forwarding logic in the switch without making any dangerous changes to the MAC or IP address. First, I have a quick overview of the workflow and the core concepts of the P4 switch. The P4 switch has separate ingress egress pipeline connected by the traffic manager, which is responsible for stuff like queuing, congestion control, packet replication, scheduling stuff. And the pipeline mainly consists of a parser, which converts packet data into metadata, and a sequence of match action unit, which operate on this metadata, and a metadata bus that carries the information through the pipeline. Finally converts the metadata back into serialized packets. The P4 program can describe the way of how the packets are passed and matched and what actions are taken. And the program will be compiled down and optimized to run at a full line rate on a P4 program switch. And with this, we can redefine the packet format for switch QE, and here it is. So now, we do not need to make any changes to the Ethernet MAC addresses, and just use a normal IP address. Like still the clients are agnostic to the existence of a cache and always use the backend as the destination. We build our application still on top of UDP and only need to reserve a port number for the key value storage service. And we can define our own packet header for switch QE with a type like different types like a read, write, delete needs. Note that the cache miss here only occurs due to very rare cache collision or temporarily outdated switch table entries. So when a cache server got a requested key, which is not cached, they need to send the query to the corporate backend and modify the type to miss. This occurs only like very rarely. And the key hash, we can define our own key hash with 64, 128 hash value as the key. And here's a quick example showing that how to program the switch key in P4. We can just define this P4 header, the key header with a type and a key hash. And when we pass on the UDP and select on the match on the destination port, and they say like our reserved port will continue to pass the key to extract our key header. And in the ingress pipeline, we can see if it is a valid key, that means it is a switch key request, and if the type is read, then we apply the cache lookup table. And in the cache lookup table, it only needs to match on the to have the exact match on the key hash, and if there's a hit, we will apply the action cache hit. And I'm making the cache hit action here. Basically, what cache hit does is just to change the destination Ethernet or IP address with the cache server. So we can see that it is very easy to write a P4 program to implement our customized content-aware routing protocol. And the people compiler also generates the API that the control plane uses to communicate with the data plane from the people program, so that our local remote controller can easily modify the table. Now let's come to the control plane. Another critical problem of the system is how to keep the cache and the switch rule updated efficiently. There are new challenges for switch KV to achieve this. First, the cache in switch KV is small and may only serve a small portion of the queries. As a result, we cannot apply traditional cache admission policies that tries to add each recently visited key in the backend to the cache. So this would introduce like very high cache churn and system overhead. And second, since each cache addition or eviction requires a switch table entry update needs to go through the control plane. So though the switch hardware can match on those keys, but once you really want to insert or delete entries, it will be much slower. So it directly limits the cache update rate, which affects how quickly switch KV can react to workload changes. Therefore, we need mechanisms that can update the cache as soon as possible while still react quickly to workload changes. So we designed new hybrid algorithms in switch KV to achieve this. First, each backend runs a very efficient load tracker to track its hotkeys recently and periodically send this report to the cache node. So the cache node aggregates the reports from all these backends and select the keys from these reports to add to the list based on its own load statistics. So this would prevent adding non-hot keys into the cache. However, these periodically hotkey updates may not be able to react quickly enough to frustrate workload changes. So we also have each backend that detects the keys that suddenly become very popular through a simple small circular counter and instantly add them to the cache. So by combining these both techniques, the cache and the switch rules can keep updated with very low overhead. And now let's go back to the beginning of this talk.
So the controller before, is it like a normal controller?
If it's like our current prototype implementation with the OpenFlow switch via OpenFlow controller, if you're using a people switch, as I said, the people compiler will generate this level of APIs. So you can call this API whatever way you like through like RPC, all to implement some or integrate this with the current OpenFlow controller. It's pretty easy to use this people generate API to add to the table entries.
And if now I'm adding more backends of cache, how many updates do you actually need to make to my controller? Because I'm assuming this controller needs a full view of the entire network, right? Not to be able to do context-aware networking. So like that I add now more backends in another cache. Like how much?
Yeah, so the controller because this controller only like receives some these node statistics. Like it's just like the normal server, it can scale pretty well because there's not much traffic going through it. But if you really have a large, big cluster, of course you have multiple controllers, and each controller just I would prefer just to let each controller be responsible for set of the partition, the backend and the switch at the end.
This cache and backend is it standard
No, so we implemented our own cache because so the non-cache is mainly for like the large cache cluster. Of course, you can use non-cache. So any like in-memory key values or fast in-memory key values can be used like cache. So you just need to add these node statistics or these cache admission policies. same as the backend, you can use like a standard backend software storage software stack. And you have to add this with like Octane node tracking or the circular handler for the first tracking. Okay. So remember, we have another challenge we want to face is that how to achieve maximum parallel in multiple systems for large-scale key-value systems. And so there are two different access models. We all know that concurrent access and exclusive access. Well, concurrent access is used by many key-value systems because all ports share the same data. It supports more generic abstractions. However, it requires careful data structure design and algorithm engineering to achieve high concurrency and also make sure everything behaves correctly. So this would especially be a problem for switch key, since as I mentioned, like we have to let the either the both the cache and the backend run all this kind of node statistics. So it will be make more complex if you want to implement a multi-server. On the other hand, exclusive access has been well studied and proved to be very efficient for network key-value store. So by partitioning the data, each core can exclusively access its own partition in parallel without worrying about any inter-core communication. However, load imbalance across different cores may hurt the system performance, which is a common criticism for this partition-based mechanisms, and it requires efficient mechanisms to deliver the request to the right ports. So again, we can use the programmable data plan in each server to maximize this parallel. So we can have like this programmable mix and use the Intel DBDK to deliver the right service to the right port. We call the flow director. Based on basically it can match on the packet headers and have some flexibility to let you define the header field. And based on this, the different receive key in hardware and send this to different ports. Both we can do it. So this is a solving a problem for the file. So we can either like the backend or the cache can be multiple servers, and in both cases we can use this to either for cache or backend we can do like partition the data, local data by port.
If you want.
Yeah, and also later that our system is actually a very good fit for this.
If you want to be top K, like suggested from the system you needed from every core and combine.
So with this we can run this like a load on load track and a counter on each, so we can ensure that high performance and correctness. And the concern of this approach is what is this load of causes different cores are imbalanced. Fortunately, with our switch TV design, the backend nodes do not fit high speed because we are like a system to guarantee backend load balance. Or you can view as, remember the n log n is the back number of cluster nodes. You can view like n as the number of cores, total cores in the cluster. And ensure good balance across all these cores, so that it's the perfect fit to just partition the data across these cores. And for the cache node, we can like the standard, either like a very commonly used technique, like use CPU caches or packet burst IO in GDDK to accelerate the performance when the workload is strict. Okay, now I have a quick look over the evaluation. This is basically on the prototype we implemented for the NSDI. So it's an OpenFlow Switch version. And we mainly ask 3 questions. How well how well does the fast small cache improve the system load balance and throughput? And does the switch TV improve system performance compared to the traditional architectures? And can switch TV react quickly to workload changes? Great. In the like the OpenFlow version, actually to the prototype. To be frank, we didn't concern too much about this, like routing domain, just have a prototype and people everything. But with the people version, so it's everything is on top of UDP. So you can do. I don't think you need to make the assumptions for the analyzing of that. The people that so in the people that we do not need to make any schedule changes. The only thing we need to do is to reserve a UDP for. So all others are after that. So all other lattice switches we can just resolve packets from the normal L12 read whatever calculate the length. So that's what's great about the program. So only we can define our own application level and the left match. So we first build a reference target backend server with ROX3D with 120 million small p-value pairs and measure its performance against the client over 1 gig link. The backend could serve about 100,000 queries per second on average. So while we do not have the resources to build hundreds of these servers like we are with the Princeton, so we choose to emulate backend based on this user performance characteristics for large scale experiments. So our test bed consists of 4 servers, so 4 server machines and 1 OpenFlow switch. Each machine has 16 cores, 32 gig of memory, and is connected with the switch through 40 gig Ethernet ports. So we use 1 machine to serve as the client, 1 machine as the cache, 2 machines to emulate many backend nodes based on the previous real backend benchmark results. So here are the parameters. We are emulating 128 backends with 100,000 queries per second for each backend. The key space is 10 billion, 16 by key, 125 values. The speed with distribution and 1,000 and 10,000 cache entries by default. So in our paper, we also include the results from other different second combinations. Yeah, we use Intel DVDK to efficiently transfer packets and modify packet headers. And in order to track the real-time system performance, so we let the client adjust the sending rate by tracking the loss rate and always keep the loss rate between 0.5% and 1%, so that we can know that what's the maximum throughput we can get when workload changes. Let's first have a quick look on the how a fast small cache can improve the system load balance and throughput. So this shows the aggregate throughput of 128 backends under workload with different speeds. So we can see that the aggregate throughput decreases as the workload becomes more skewed. Because there are some few servers that just bottleneck and make all the systems stop. But by adding a single cache node to serve 10,000 hotlist keys, so the load across backend can immediately becomes balanced and reach its maximum capacity. So the cache throughput, which is the red part, increases as the workload becomes more skewed. So this shows that the small cache is very effective for back-end load balancing. So as it proves that what we previously mentioned, that by only adding the small cache, we can always guarantee that the backend can be fully utilized no matter how skilled or changing the workload is. And here we show how switch queuing improves system performance compared to traditional architectures as the cluster scales up. So in the traditional architecture, the system throughput would be quickly bottlenecked by the cache throughput, because all queries have to go through the cache first. In switch queuing, we can keep near linear scalability, because the cache node does not need to process queries that should be served by the backend service. And these two figures show how switch queuing minimizes the query latency compared to traditional architectures. You can see that switch queuing has a much lower latency, especially the 99% tail latency. This tail latency often determines the real service quality. And again, we can see that switch queuing has high throughput latency, higher throughput capacity than other architectures. Limit. So let's take a quick look on how switch queuing performs as a workload changes quickly. Here we make 200 code keys become the hottest keys every 10 seconds. This is a radical change pattern. We can see that the traditional method performs really fast. And the performance is much better with periodic updates, but it still cannot recover quickly enough when the workload suddenly changes. So by additionally adding the birthday hotkey reports, the system can react very quickly to the workload changes and always with near optimal performance for most of the time. In the paper, we also have results showing the performance under different workload change patterns, and also the switch queuing has good benefits from its cache update
What's the period of clock outputs? Is it exactly the same period as your workload? You mean not maintaining the So the work in your experiment, the workload changes every 10 seconds?
So this is every 10 seconds. Oh yeah, you mean like the top case, like what's the duration of top? Yeah, we have this. So basically applies a heavy data algorithm, and we also use time segmented and do something like a moving average. So it's basically, so it's most values, so that parameters can change, but in our setting, I think during the last 1 or 2 seconds, basically it's a traffic top algorithm plus a moving average.
Sorry, what I mean is how often do you
That
class is very periodic.
Yeah. So it's, I think it's 1 second or 2 seconds. 1 2 seconds. Every 1 second.
Why is there a dip in the graph like every 10 seconds?
Oh,
like
this is
bottom?
because our workload, as in like every 10 seconds, the workload.
Even with the bursty hotkey updates, like you wouldn't expect it to be.
Yeah, you still have to wait for a little while, like if there are this cache updates going on.
So all the bursty updates are coming at the same time, is that right?
Yeah. Yes, this is the setting for the system. Yeah, all the things. So it's basically a sudden change. In the paper, we also have like more like a random change, some constant random change or other change patterns. These are the paper like this radical change pattern. Okay. So in conclusion, CPV is the fast and cost-efficient key value store. It uses fast small cache to guarantee backend load balancing, and it has efficient content-aware programmable network switching to ensure the system has low tail latency, scalable throughput, and high system availability. It can keep high performance under highly dynamic workload and meet the service level agreements in terms of throughput and latency very more efficiently by performing cloud services. Good. Thanks.
So what if you don't have gas and security? I would imagine this probably having that in.
Well, that if you don't have cache, if the workload is filled, then this is the throughput you can get for filled network. So yeah, if the workload is evenly distributed, it's of course you can get it linear. So what we are trying to do is to keep this linear scalability and handle this skilled workload. Okay, what I haven't included in the slide is actually that we are exploring like extended to like in-memory backend caches, because as I mentioned in this cache switch architecture, you can define your own packet headers. Actually, seeing it is actually possible to put the entire key value in the switches. That is the experimental project we are going on, because as I said, for many keys, only like tens or hundreds of bytes, it is possible to define a people program to serve some extreme hotkeys directly from the switch. So that would be very interesting stuff.
What is this app?
Oh, it's just like a power law distribution. Basically, like usually say 1% of your queries may account for like 80-90% of your 1% of the keys may account for like 80-90%.
So that's a point.
Yeah, it's like just versus my case versus Obama's case. This kind of.
You could have to change the model
We had a discussion of the consistent model. Basically, our goal is to maintain the strong consistency between the cache and the backend. So whenever a write update request will first come to the cache, always directly go to the backend, and the backend can immediately update the cache and then return to the client. So I'm going to guarantee a strong consistency. This is actually another benefit of switch queuing, because in other systems you may argue that we can maintain a small cache in each client level. Each client has a small cache, and then we may be able to achieve a similar load balance effect. But in that case, it's very hard to achieve this cache consistency. Okay.
These tests you were doing, these type of
In the paper we have, we have right to do, we have right, This is only this is a read only. Because the loading balance is mainly for read, so the write request has to go to the backend anyway. So you cannot balance this write. And on the other hand, the write is not that skilled.
We're out of. We have maybe time for half a question more, but basically we're out of time. But you can talk to the speaker after you talk.
Thank you very much. Thanks.